Okay, so I will briefly review what we learned. So, so in the previous class, so we learned about the sequential logic, and then actually there are two types of digital logic: the combinational and sequential logic. And then I mentioned that until the midterm exam, we learned about the combinational logic, and then after that we will learn about the sequential logic, and then also. So you need to understand the definition of the sequential logic, the combinational logic. In the combinational logic, the outputs are determined by only input signals, it's a current input signals, but you need to you need to understand that sequential logic has memory, which means that the previous states or previous input values can be stored. Okay, it's stored in the sequential logic, and the outputs are determined by previous and current. The previous means that it's the states of sequential logic. So you need to distinguish between the combinational logic and sequential logic. So, okay, then so. We started from the bistable circuit, and then bistable circuit means that the current value can be stored. So actually, I mentioned that this is just a memory. It's actually this is the circuit of SRAM actually. So you know there are two types of RAM. So the random access memory. Actually, the popular type is the DRAM, and then so we can use the SRAM. But you know, this is the circuit of the SRAM. So which means that the values, the current value can be stored, kept inside of this bistable circuit. But I also explained that in the bistable circuit, we cannot control the values. So which means that there is no input. There are no input ports in this bistable circuit. So which means that we cannot control the values stored in this bistable circuit. And then so we can modify the bistable circuit to a sound bridge. And then so if we just understand the meaning of S and R, then also we can understand the purposes of input ports. So R means reset. Actually, this is very important in the digital logic. So usually R represents reset, and the reset means that it makes signal 0. Okay, and then set means that it makes signal 1. Okay, so there are two inputs, S input and R input. The SR latch. So using these S and R inputs, we can control the values. Okay, the values inside of this latch. So I explained the meaning of this NOR gate. So usually, so actually the bistable circuit, we use inverter, it's a NOT gate, but we need to control the values inside of this bistable circuit. So we have two input NOR gate, then the one of input of this NOR gate are connected to the R input and S input. Okay. And then if you, I believe if you just understand the behavior of the gate, and you can also easily understand the behavior of SR latch. So actually there are 4 possible cases by inputs of SR gate. Then so if we just figure out the behavior and output of this SR latch using these 4 input cases, then we can easily understand the behavior of SR latch. And then also from this SR latch, we can also define another type of a latch. This latch is called lead latch. So in this D latch, you can find the two different signals, two inputs, the clock and B. Okay. So actually this clock signal is very important signal in this type design. So if you just see the CPU specification, then you can find the clock frequency. So clock signal. So clock frequency. In the specification document also represent this clock signal. But so actually in the today's class, we will learn about the flip-flop. So and then I explained that we do not use latches, okay? But we can implement flip-flops based on latch circuits. So that's why we learned about the latches. So anyway, so there are two inputs, clock signal and D. So D usually they represent the input of this flip-flop. So D means the data. Okay, then clock is just a clock signal. So clock controls the state. Clock controls the state of this D latch, and then D is just data input. So this is the symbol of the D latch. This is the clock signal, and then D is the data input, and then there are two outputs, Q, for the Q and Q bar. Okay, so Q bar is just the inversion of this Q. So you can understand that a clock signal is just a control signal, and then D is reflected to Q based on this clock signal. Okay, so this is the function of the latch. Okay, you need to understand the function of the D latch. The clock is 1, then D is just reflected to Q. So which means that it looks like the Q is just connected to D. Okay, so Q is equivalent to D if the clock signal is 1, and then if the clock signal is 0, then the value of Q, the output value is just kept or maintained inside of this D latch. So it works like memory. Okay, so it works like a memory. So this is the D latch circuit based on the RS latch. Okay, so the AND gate is connected to the two inputs of RS latch. Then using the D, then we can also control the output Q. So in SR latch, then we can control the output value Q using the R input and S input. So which means that we can just control the Q using the D. And then the clock signal is also one of the input of D. And then because it is AND gate, then we can just control the enable or disable of this key using the clock signal. So the A and 1 equal A. So which means that this is just enabled the circuit by AND gate, and then the A and 0 equal 0 regardless of A. So which means that the circuit is just disabled. Okay, so A can be transparent to the output of AND gate if the one of input is 1 is transparent. A is just equivalent to the output of AND gate, or if we just set the one of input of AND gate as 0, then it's disabled. Okay, so we can use AND gate for this approach. So which means we can implement the latch using SR latch. Okay. Okay, this is the, and then also I show the example implementation of the latch. So we can use the always on the latch statement for implementing latch. But you need to remember that usually, actually we use latch for special circuit. And then in this the design, we do not use latches. Okay. So, so actually there is a syntax for latch design, but we do not use latch usually. Okay, so now let's learn about the flip-flops. It's a new circuit that, but and actually flip-flops are frequently we frequently use flip-flops. Okay, so then let's see why. Okay, so we will learn about the D flip-flops. So you can notify the name of the display flip, and then actually you can find that this D flip-flop is the name of the D flip-flop is similar to D latch. So actually the behavior is very similar, but it's also different. Okay, so and then so you need to understand the differences between D flip-flops and D latch. Okay, so there are two inputs like clock signal and D input. And then the meaning of D and clock is also the same. The clock is used for controlling behavior or state of is D flip-flop, and then D means the data input. Okay, it's the same to the D latch. So this is the symbol of D flip-flop. So you can find that this is the clock. It's a clock. It's very similar to the D latch. And then D is the data input. Then also you can find the Q and Q bar. So you can find that only this symbol, like the triangle, this triangle symbol is just different. Okay, the clock is just even to this different graph, you can find that you can find this triangle symbol for the input of clock signal. So then let's see the functional specification of D flip-flop. So you need to understand this functional specification. So it is because the functional specification is just the definition of our this module, right? D flip-flop. So this is the function of D flip-flop. Sample D, okay, sample D on rising edge of clock signal. So what does it mean? So we need to understand the behavior of clock signal. So what is clock? The clock is a 시계 in Korean usually. So it's like the tick tock, tick tock, tick tock. So the clock, those clock sounds like tick tock, tick tock, tick tock. Right. So you know the clock includes the second the choчин, like it's a second needle. So actually the clock using a clock generate the repeated rising and falling signal. Okay, tick tock, tick tock. So it's just a real clock. So like this tick tock signal, the clock is the repeated rising and falling signals that look like this. Okay, so this is the signal with this high signal means the 1 and this is the 0. So which means that the clock signal repeatedly represent 1 and 0 signals. Okay, and then this is the repeated signal. So this signal is repeated using the same period. So which means that this T, this is called a period of clock. So which means it's the, so you know, in the clock signal, this part is just repeated, right? This part is repeated, repeated, repeated. So we define the period or time between the this repeated part as its period of clock. So for this period of clock, the signal of clock is just repeated. Okay? The same waveform or same signal behavior is repeated in this T period. So this time is also T. It's also T. This also this is the time for this period is also T. The same period. Then what is the clock frequency? The frequency is the inverse of period. So F is equal 1 over T. So it means that, so you know, if you see the smartphone, so the specification of processor, then you can find clock frequency like the you know, if you are interested in the processor design or processor specification of your smartphone, then you can find, oh, this smartphone includes Qualcomm Snapdragon, blah, blah, blah. And then clock frequency is 2.4 gigahertz. It's frequency. So what does it mean? So giga means 10 to 9. So which means that this period is repeated 2.4 multiplied by 10 to the power of 9 times within 1 second. So that, so actually, so you know, the unit of this T is the time, the second. So frequency is the unit of this frequency is the 1 over S, so which is the hertz. Okay, hertz in Korean, hertz actually, hertz. So the frequency represents this part. So one period of clock is repeated n times. So which means the n hertz in frequency. Okay, so you know, this is the clock signal. So clock signal repeating the 1 and 0. So this rising and falling of signal are repeated again and again in the circuit. So this is the clock signal. Then what is the function of D flip-flop? So you can find the rising edge. So what is the edge? The edge is this one, okay, and yan in Korean. So rising edge means you can find so many edges here. So rising edge is this one, okay, this one. So rising edge means that the signal is changed from 0 to 1. So and then we can find some edge here. So this is the rising edge. And what is the falling edge? Falling edge is this one. Okay, it's a falling edge. But so you can find the sample D on rising edge. Rising edge of clock. So which means, so this is the rising edge of the clock signal. So at this point, D is sampling. So sampling means that the value of D is the sample. It's checked and then stored. Okay, so which means that So at the rising edge of the clock, this circuit detect the value of D, and then this value of D is stored. You know, this is the sequential logic. The value of D is stored at this point, the rising edge of clock. Okay. So this is the deep learning. So, and then this sampled data is reflected to the output of deep learning. Output is Q. So which means at the rising edge of the clock, this is the clock signal. At the rising edge of the clock, the value of D is sampled. So it's detected and stored, and this D is reflected to the output. Okay, this is the function of deep learning. Otherwise, so we define the behavior at this point, right? The behavior of deep learning at this point. Then otherwise, for other cases, like these cases or this cases, it works like a memory. So which means that at this point, at the rising edge of the clock, the D is sampled. Then in other cases, this sample data is just maintained. So it's just stored. It works like a memory. Okay, do you understand? So only at this point, the D is sampled, so it will be the value of D detected and stored. And then for other cases, so for this period, just this sampled value is stored inside the different number. So that is the behavior or functional specification of different number. Okay. So, and then this behavior of different number is called edge trigger. So because the input data is sampled at the rising edge of clock signal. Okay. So let's compare with the latch. So this is the behavior, the truth behavior of the latch. Okay, so you know this is also a clock signal, so which means that you can understand that the signal is just repeated 1 and 0, 1 and between 1 and 0. The clock signal is 0, and then this is 4. But clock signal is 1 and Q is equivalent to D. So which means so this is the clock signal, and then during the clock signal is 1, and the Q is just D. Okay, so this is the behavior. But D flip-flop is different. Only at this point, Q becomes D, right? So it's just different. So in the latch, during this period, it means that during the clock signal is 1 and Q is equivalent to D. But the D flip-flop, only at this point, the rising edge, during this rising edge of the clock, the Q is equivalent to D. Okay, this is the difference between D flip-flop and the latch. And then I said that we frequently use D flip-flops in digital systems or digital circuit. Okay. And actually, you can implement D flip-flop using the latch. Okay. So you can find the 2D latch here. Okay. So so this is the clock signal, and then clock signal is the two D latches are connected in serial, and then this clock signal is directly connected to the clock port of the D latch. This is a latch, and then the inversion of clock signal is connected to the clock port of the D latch. So let's see the behavior of this circuit. Okay. So when clock is zero, then this becomes 0 and this becomes 1. So which means that, oh, this is transparent and this is memory. So then at this point, when during the because this clock port is 1, then N1 becomes D, right? But how about the Q? Because this signal is 0, then D is not reflected to Q, so which means that Q just maintains the stored data in this L2 D latch. Okay, so D is just here. Okay, and when the clock becomes 1, so it becomes 1 and it becomes 0. So when the clock is changed, then this becomes the memory, and then this becomes the transparent. So when the clock, so during this 0, the D is just stored, so D is just transferred to this N1 during the clock signal is 0. And then when the clock is just changed, then this D is, the clock becomes the 1. Then D is here because this is just a memory. Okay, so D is not reflected to the N1. Okay, this N1 just stores the value when the clock is 0. Okay, but at this point, the Q becomes N1. Okay, do you understand? When the clock becomes 1, then Q becomes N1. So it becomes transparent. So what does that mean? The clock signal looks like this, like this one, like 0 to 1. Okay, so when the clock signal is, while the clock signal is 0, then this D latch becomes transparent. So this D latch just reflect some input D during this one. But because this D latch L2 is opaque, so which means that it works like a memory, so this change of D is not reflected. So this L2 just maintains the previous value. Okay, so it's just this D value is just reflected to this N1 during this period, but during this period, this L1 works like a memory, so D is not transparent to this L1, but you know, in N1 just stores the previous, so this value, the values of D during this period, right? So N1. So this value is just reflected to this Q. You understand? So at this rising edge, this value of D is sample, okay, and then its value is reflected to Q, okay. So let's see the waveform, of the latch and the deep flip-flop. So, I just explained that you need to understand the behavior or differences between the latch and deep flip-flop. Okay, so let's see the waveform of. So this is the clock signal. Then also this is the D, and then the first law of this waveform is the latch. The Q, the output of the latch. Then, so in the latch, the output Q is equivalent to the while clock is 1. So it means the latch become transparent if the clock signal is 1. So during this time, the latch becomes transparent. So what will happen? So during this period, so this is the D. The D is changed like this. So it's transparent. Okay, during this period, also during this period. So the Q is the D will transfer to the output Q only during this period. Okay, this period and this period and this period. So during this period, the Q is just maintained. Okay, it's 1 to maintain, and then the latch becomes transparent during this period because clock signal is 1, right? So it's just same to the input signal. Okay, and then during this period, the clock signal is 0, so which means it's opaque. So the latch becomes opaque. So it just looks like memory. So Q is not changed during this period. And then this is just 1, and this the output is just same to the input. So if you can understand that if the clock signal is 1, the output is just same to the input to the latch. Otherwise, the output is just maintained. So in this period, the input signal is changed, but output is just maintained. So this is the behavior of the latch. Then how about the flip-flop, the flip-flop? So we need to focus on edge, the rising edge of the clock. We need to consider only the rising edge of the clock signal for the flip-flop. So I explained that the input signal D is sampled at the rising edge of the clock, and then this sample value is transferred to the output of the flip-flop. Okay, so Q is also D, but only at this point, at the rising edge of the clock. So what will happen? So in this for the flip-flop, so this is the rising edge, this is also the rising edge, this is the rising edge of the clock. At this point, D is 0. So it's 0, and otherwise, so other period, it's maintained, just maintain. And then at this point, it's also the rising edge of the clock. D is 1. So which means it's sampled and it becomes 1. And then also otherwise it's maintained. Okay, so this is the behavior. And then it's maintained until the next rising edge of the clock. So in this point, the need one or is one equal one. So it's maintained. So this is the behavior of the flip-flop. So I believe you can understand the differences between the latch and the flip-flop. For the latch, we just check the signal value of clock. So if the clock is 1, then the Q becomes D. But for the D flip-flop, we just check the edge, the rising edge of this clock signal, and then samples the value of D at this point, that rising edge of clock, and then Q becomes D. Otherwise, Q is maintained. Okay, so this is the different behavior between the latch and the flip-flop. Okay, so I think I believe you can understand. Okay, so this is the completely waveform by the latch and the flip-flop. Okay. Then how can we implement the flip-flop using system variable? So you can find the signals, the clock and the Q. Then in order to implement the flip-flop, then you can use the always underbar FF statement. So FF means the flip-flop. Okay. Yes. So I also frequently use FF for representing flip-flop. So flip-flop. So always underbar FF. So in order to implement the flip-flop, you can use the always underbar FF, and then also you can find the at sign here. And then this is the sensitivity list of always statements. Then what does that mean? So as you can see, you can find the COSE edge clock. So it means the positive edge of clock. And then positive edge means the rising edge. Okay. So inside of the sensitivity list, we can find positive edge of clock. So which means that it's the rising edge of clock. So not always statement if the sensitivity list the signals in actual conditions in sensitivity list is true, so it's met, then this always statement, the inside of always statement is executed. So what does that mean? We use the always on the method, it means the flip-flop, and then the sensitivity list, it's the positive edge of clock. So which means at the rising edge of the clock, right? Then this is executed. Okay, this is executed. So definition. So behavior of this statement isn't same to the functional specification of the flip-flop. At the rising edge of the clock, Q becomes D, right? Otherwise, it's just maintained. So we just define the behavior at this point. So at the positive edge of clock, actually this means also M. So it's already good. So it represents M in English. So already on the at positive edge of clock, then Q becomes D. So this is the implementation of a flip-flop in system very long. So it's very easy, right? So as you know, so as you can expect, so there is also another edge, so negative edge. So negative edge represents the falling edge. Okay. So So additive or negative. So we can also use the negative edge. So negative edge represent falling edge of this clock signal. So this is the implementation of deep flip-flop. And then also, so I said that in digital system, we frequently use deep flip-flops. This is because at the rising edge of the clock, deep flip-flops can store input signal. Otherwise, that's a simple input signal. Otherwise, this Q, the output Q is just maintained. So that means we can control the flow of signals in digital systems using deep flip-flops. Why? So this is the input signal. It's like a dam. Okay. So the input signal can be changed like this, but only at the rising edge of the clock. So we sample the input signal here, and then this input can be given to other modules. Okay. So which means using the deep flip-flops, we can control flows of signals. Okay, that's why we actually deep flip-flop is the very critical part, very critical module in the digital system. Okay? We frequently use this deep flip-flop. So which means, so actually when we learned about the basic signals, then we also learned about the vectors. So which means that the group of signals. So like the A3 down to 0. So we frequently use these group signals in order to represent the large value or large data. Right. So in order to represent the large number, then we require the large number of bits, right? So if we use multiple flip-flops to store or to sample input data, then these multiple flip-flops are called a register. Okay, this is a register. So in this figure, you can find 4 flip-flops here. And then so each bit of input, or each bit of D is connected to the input of deep flip-flops. And then you can also generate the multiple bit of Q. Okay, multiple bits of Q. So we can also, so which means that we can also connect the multiple bits of input signal to the multiple deep flip-flop, and then this is called a register. Okay, we frequently use terminology register in the system design, and then this is the symbol of the register. So as you can see, the multi-bits signal at T3 down to 0 is connected to the input of register. Then it generates the multi-bit signal Q 3 down to 0. And then we frequently use this symbol and as a slash and number, and it means that this symbol represents the width. So width of signal. Okay. So it represents the 4 lines. There are 4 lines for this input signal. Okay. The 4-bit input signal. So we can use this register symbol to represent the multi-bit deep flip-flops. And then how can we implement the multi-bit deep flip-flops? It's simple. Actually, it's simple, right? So this is the clock signal. So, but as you can see, the same clock signal is connected to the each clock port of deep flip-flop. So which means that the bit width of clock signal is just 1 bit. So that's why I use the clock signal is declared as 1 bit signal. Okay. Then the D and Q are declared as a multi-bit signal. The 3 down to 0. It means 4-bit signals. Then it's very simple. So it's the same. And then Q is equal to D. So it's like this. The Q is equal A and B. So it is the bitwise AND. So it means that each bit of D is connected to the Q. Okay. So we can simply implement the multi-bit D flip-flop. So it means that each register for these multi-bit signals. Also, we can implement the different type of D flip-flops. So the first type is the enabled flip-flop. So enabled flip-flop means that the sampling of input signal is enabled if this EN signal is 1. This is the definition of enabled flip-flop. So this is function. If enable is 1, then it has to the Q at the clock edge. If the enable is 0, then E is not transferred to the Q. Okay, it's very simple. Okay, if EN equal 1, then E is Q, else E actually Q is maintained. But you can find the clock signal here. So at the rising edge of the clock. So enable the flip-flop means that at the rising edge of the clock, we just check the EN signal and D signal, and then if the EN signal is 1, then D is sampled and the still D flip-flop. Otherwise, so D is not reflecting the Q. So this is the equivalent circuit. Okay, so we can find the 2-to-1 multiplexer here. So and then the output of the 2-to-1 multiplexer is controlled by enable signal. Okay, so which means that if the enable signal is 1, then D is just connected to the input of D flip-flop. Okay, it's the same to the normal D flip-flop. Otherwise, if enable signal is 0, then the Q is feedback to the input of D, which means that the Q is just maintained. Okay? So this is the symbol of enabled flip-flop. We can also implement enabled flip-flop using system variable. So this is the implementation of enabled flip-flop in system variable. So actually, only this part is inserted if enable. So which means that if enable is equal to 1 because it's true, then Q becomes D. Okay, but also we can observe sensitivity list of already statement like positive edge. So which means that this statement is only activated with the rising edge of the clock. Okay. At the rising edge of the clock, we check the enable signal. So if enable is 1, then Q is equal to D. Okay. Otherwise, Q is just maintained. Okay. But this is not defined inside of the already statement. Okay. It's very simple, right? And we can also use resettable flip-flop. So this resettable flip-flop includes reset signal. So what does that mean? So reset if a reset becomes 1, Q is just also becomes 0. Okay, this is the definition of a reset. So I also explain the definition of the meaning of a reset signal when we learned about the SR range. So reset it becomes 1, then Q it becomes 0. Okay, and then if reset is 0, then it stays to the no behavior of normal equilibrium. Okay, so the reset is 1, then regardless of the input signal, then Q becomes 0. That is the behavior of a flip-flop. So actually, in the system, we use this resetable flip-flop. Reset is very important in the digital system. It is because, so you know, so sometimes we just turn off our electric devices, right? We turn off which means that we turn off our TV or refrigerator, so electric devices. Then, when the device is turned off, then the devices need to be in the stable state. Okay, but if we just disconnect the supply voltage or supply wire to our electric devices, then devices can be the unstable state. Okay, then when you turn on our electric device, then this unstable state can make undesired behavior of our digital system. So that's why when we design digital system, then we just define reset state. Okay, and then reset state can be implemented using resetable flip-flop. Okay, so this is the reset. But there are 2 types of reset signal. So it's a synchronous reset signal and asynchronous reset signal. So you know, the synchronous or asynchronous, this A represents the not. Okay. So synchronous reset means that the behavior of reset. The behavior of reset is defined only at the clock edge. Okay, so it looks like this. So this is the example of synchronous reset. So you know, the D is connected to one of the input of AND gate, and then this reset signal is connected to the another input of AND gate. You know, you can find the reset bar. So what does that mean? So reset signal is 1, and this becomes 0, and then this becomes 0. So Q becomes D, but this Q becomes D, the rising edge of the clock. So the behavior by reset signal is also synchronized. So it reflects the behavior of reset signal is also reflected to Q at the rising edge of the clock. So this reset is called a synchronous reset. So synchronous means that the behavior is determined only at the rising edge, right? At the rising edge or falling edges of a clock signal. It means synchronous. So which means synchronous reset means that the reset behavior is determined at the rising edge of the clock. It's synchronous. Then I explained that A represents not, right? So asynchronous means that the reset is not determined by clock signal. So which means reset is immediately reflected to Q. Okay, this is the asynchronous reset. Okay, so there are two types of reset: synchronous reset and asynchronous reset. Synchronous reset means that the behavior is determined at the right edge of the clock. Asynchronous is just not synchronous. Okay. So this is the example of asynchronous resetable deep report. Okay. So actually you can find the reset signal here, and now this is P and Q. Then observe the clock signal. So asynchronous, async, so which means that the reset signal works regardless of clock signal. So which means that we need to also define the condition by reset. So if we just compare the normal flip-flop, so you can find only the positive edge of clock in the sensitivity list, but for the asynchronous resetable flip-flop, then you can find another sensitivity list, it's negative edge reset. So you may think that, oh, if we just use the reset, not negative reset, then you may think that, oh, it's okay. But usually, so it's just to remember, just to memorize. Not to implement the asynchronous reset, then we just use the sensitivity list using negative reset or positive reset. Okay? Just memorize. Okay? So this is the example of the asynchronous negative reset. So it's a negative. So which means that if reset becomes 0, okay, becomes 0, then it goes to the reset state. Okay, it looks like so. It looks like so. If the reset becomes 0, then reset is enabled. Okay, so that's why I use the negative edge reset. So it's a negative reset. And why do you use negative reset actually? So negative means that if a reset is 0, then it's enabled. The reset state is enabled. So the meaning is inversed. Okay? It's a negative reset. So why do you use the negative reset? So it is because usually when I explained that we need to define reset state for the state of electric device when the electric power source is disconnected. So which means that electric device is turned off, then we need to define the state of this electric devices. So turned off just to represent the disconnection from supply voltage, but it also means the supply voltage becomes low voltage. Okay, and so which means so there is the VDD and then ground in this electric device, but if we just disconnect the power source to the VDD, which means that the switch is turned off, then VDD just becomes the ground. So it means 0. So usually when the electric device is turned off, then the signal becomes 0. it's also same to the reset signal. So the counter off, reset signal becomes 0. Which means that we need to define the reset state when the reset signal becomes 0. That's why we use asynchronous reset in distance systems. Okay, you understand? So when the distance of electric device is turned off, then usually the reset signal becomes 0. Then we need to define the reset state when reset signal becomes 0. Okay, that's why we use the negative reset. So this is the behavior model of in flip-flop with an asynchronous negative reset. Okay, asynchronous negative reset. And therefore, not to implement this flip-flop, then we need to add the sensitivity lead for this signal. Here, the negative reset. Then we need to define the behavior by reset signal. So if inversion of reset, so that means that if reset is 0, okay, because you can find the inversion here. So it means that if the reset signal becomes 0, then Q becomes 0. Okay. So this is the reset behavior of this flip-flop with asynchronous negative reset. Understand? Otherwise, else, this is the behavior of normal flip-flop. Q equal E, but at the positive edge of clock. Okay. So if you see that this always statement, then you can understand that this always statement is activated at rising edge of the clock or at negative edge of reset. So which means that if the reset signal becomes 0 like this, then this already flip-flop is activated. So this statement is checked. So negative reset, so reset becomes 0 here. Then we check the reset signal. If the reset is 0, then Q becomes 0, all zeros. Otherwise, then this always flip-flop is activated at the positive edge of clock, the rising edge of the clock. But at the rising edge of the clock, the reset signal should be 1. Okay. Then Q becomes T at the rising edge of the clock. Okay. So this is the actually common flip-flops we use in the system. It's common flip-flop. So as I mentioned, we need to define reset state in electric devices or digital devices. But in order to implement reset state, we require resetable flip-flop. So we frequently use asynchronous negative reset in our digital systems. So this is the example of a flip-flop with asynchronous negative reset. And then we frequently use this type of flip-flops in common digital systems. Okay. So we can implement this flip-flop like this. It's a common, very common. If you see the very low code in the internet, then you can frequently find this statement that implements the flip-flop with asynchronous negative reset. Okay. So you can also define the settable flip-flop, which means that if the set becomes 1, then Q is set to 1, but it's not frequently used. We frequently use the resettable flip-flop. But we can also define this settable flip-flops. Okay, but it's not important actually. So we frequently use this type of flip-flop. Okay. Then let's learn about the synchronous sequential logic. So until now, so we learned about the sequential logic. Like we start from the bistable logic, then latches, and now deep flip-flops. And then I mentioned that we frequently use deep flip-flops in the system. So which means that by combining combinational logic and deep flip-flops, we can implement common digital systems. So you need to remember that by combining combinational logic and deep flip-flops. Okay. So why? Let's see the reason. So this is so you can find the feedback loop here, and then this is the serially connected inverters, right? Then what will happen? So each inverter has delay. So actually, this is the real behavior of inverters. So this feedback serially connected inverters. So what is the problem? In the combinational logic, so we already learned about the delays of combinational logic. Now I explained that the delays of combinational logic is determined by many factors. Okay, we cannot represent the fixed behavior. So it's the fixed delay of combinational logic in our real circuit. Is it because the delays are influenced by many factors? That's the problem. If we cannot control, if we cannot implement the controlled circuit or controlled system, then that system can be problematic system. Okay, unstable system. I mean, and then actually we need to implement the controllable and stable system. That's why we require sequential logic and actually flip-flop for implementing the system. So that is the example. So we cannot control the delay because the delay is influenced by many factors. So which means that we cannot expect the fixed behavior of the circuit, which means that the circuit becomes unstable. And then I explained that actually using the deep flip-flop, we can control flows of signals. Why? At the rising edge of the clock, the signal value is sampled and maintained for the other cases. So using the deep flip-flop, we can control the flows of signals. That's why we use the sequential logic for implementing digital systems. So this is the typical sequential logic design for people to explain this. Let's see this example. So actually, now to implement this logic, we use this form of logic or this form of logic. So what can you see? You can find the state element. Actually, this is a deep flip-flop. This is a deep flip-flop, and then combinational logic here and deep flip-flop here. So actually, I said that this is the deep flip-flop. And then this is another deep flip-flop. So, and then same clock signal is connected to the clock port of this state element, the deep flip-flop. And then between these deep flip-flops, there is combinational logic. So if you see this figure, you can find that the output of deep flip-flop is given to the input of combinational logic. And then this combinational logic, output of combinational logic is connected to the input of this flip flop. And what can we expect for this behavior of this logic? So at the rising edge of the clock, then input signals are synchronized, which means that at the rising edge of this clock, the output is determined and maintained. So for this combinational logic, input signals are determined at the rising edge of the clock and maintained, right? And then the combinational logic has some delay. After some delay, this combinational logic will generate output. Then at the right edge of this clock, its output is also sampled and synchronized with the clock signal. So using this model, the right edge of the clock, all input signals to this combinational logic is synchronized and maintained, so we can generate the keyboard input to the combinational logic. And then the delay, the output delay may be different, because it's combinational logic, but this output is just sampled, so which means that synchronized. Just at this rising edge of the flip flop. So by doing this, we can generate the table and then control system. And then usually we implement the data system like this. Okay, so I'll start here. And then let's see the next class.